So, all right, let's take a look at clustering. This is the first unsupervised learning topic. We will do clustering, but do the basics first, go through the common clustering methods. Actually, in your textbook, you will find more metrics for clustering evaluation, but it will not be covered in this lecture. For the basics, I will first offer some information about unsupervised learning and clustering in general. We will try to differentiate supervised learning from supervised learning, which we learned in the previous 7-8 weeks, and then we will see the difference. And also, I try to offer a little bit of math so you guys can see how to understand the difference from a mathematical perspective. Then we'll go through 4 common categories of clustering methods. They are center-based clustering, density-based clustering, distribution-based clustering, and hierarchy-based clustering. So supervised learning is what we have been working on intensively in the previous several weeks. And for this one, you guys know that how it works, right? We get an X, we get a Y, and X is for the unlabeled samples, and Y is for the labels. And what we need to do in supervised learning is to predict Y labels based on X, the unlabeled data. So that means we're trying to find relationships between the unlabeled data and labels. So that is supervised learning. But now we move to unsupervised learning to see what we need to deal with now. And one major change that you can easily observe is that now we only have unlabeled data samples. That means we only have X and we have no labels. So we don't have Y anymore. And if we don't have Y, then what do we need to do for unsupervised learning? What is the goal of it, right? It's not like supervised learning. You get moved from X to Y. Now there's no Y. So what do we should do? Actually, what we need to do is now define relationships between unlabeled data samples. So we have a lot of data samples there that don't come with labels. But if you plot the data points, the samples, for example, if you have 2 attributes, we know that we can plot the samples in a 2D space, right? They have different locations. Then we want to find the relationships between different data samples based on their locations. One intuitive way of doing that is that if we plot all the samples out in a 2D space, you will find at some points they're close to each other, whilst they are close to some other points, right? The may form different groups, or in here we call different clusters. So here in clustering, what we are trying to do is trying to group different samples or data points into small groups based on the relationships between different points. Sometimes we use other words such as linkage, such as connectivity between different points, but they're the same thing. But a more straightforward way of describe the connectivity, the linkage, is based on the distance, right? In a 2D space, you guys know how to do the distance. But please keep in mind, when we are talking about a distance, there are different ways of calculating the distance. The most common way is the way that we used before, is the Euclidean distance, right? You get the 2 points, one minus the other, you get the square root of the square of it. That's how we do it. And so now, this is in a 2D space. When you have more than 2 attributes, we know that when you have 3, you can still plot the samples in a 3D space. But when you have more than 3 attributes, it's very hard to do that, right? But the idea is the same. We can even have in a 4D space, even have higher dimension data spaces. We can still do it in the same way. We can still calculate the Euclidean distances between different points. And then based on how close one point from the other points, we can do the clustering. Here are 2 examples to show the idea. On the left, you can see that is for a classification task. So this is a very typical supervised learning task. You can see that we have different samples and they have different colors and shapes, right? They're represented by different markers. And these colors and markers, they are actually associated with the labels. So you know that For example, the red squares, that's the first class, and the green circles, they're the second one, and these green triangles, that is the third class, right? We have three classes, and they are given for a classification task. So what we need to do in supervised learning in this classification task is to identify the way to separate the three different classes of points. Here we just need to identify the boundaries, right? That's what we need to do in a classification task. So we are given the training data with the labels, in this case the points with different colors and markers. Then we learn the boundaries. In the future, when we are giving a new point, a sample for testing, we just need to take a look, compare them with the three boundaries to see which region it falls into. If it falls into, for example, region 2, then we say that is class 2. That's for testing. But now let's take a look at clustering. So this is a supervised learning task. And for this one, we also have different points. But if you take a look, in this case, all of them are represented using the black dots, right? So there are no labels. They're all the same. We don't know the differences. And the only type of information that is available in this case is just the location of the points, depending on the attribute values. So here there is a two-dimension problem. It has two attributes. So each point has two attribute values. That's the x, and the y-axis. That determines the location of the point or the sample in the data space. So in this case, what we need to do is to see how to cluster the three different the points. But here, because this is a problem that is easy to solve, we can even solve it using our bare eyes without any machine learning algorithms. That we can easily see that, oh, there is pretty obvious that there's three clusters or three groups of points. And if we draw a boundary, we can even separate these three. So in the future, we also need to do, for example, if you're given a new point, how we can tell which cluster that sample belongs to. That depends on what algorithm that we use. For example, one of the most straightforward algorithm that we can think of here is to identify a center for each cluster, right? Then calculate the distance. See, for example, any new given point, to see each center, it has the shortest distance from that point. Then we say that, oh, it belongs to that cluster. So this is for clustering. But we may have much more complicated algorithms for determining how to cluster the points and how to determine a new point belongs to which cluster. And a few more things that I want to make to clarify here. If you read the textbook chapter, if you read some other materials about clustering, you'll find there are a few words. Cluster, you can understand it as a synonym of group, right? And another word, that's clustering. Clustering can mean different things. This can mean the process of clustering the points into different groups. So it could be a process, or it could be an outcome. So sometimes we say that a clustering, that means we already finished the process and get something. That's the outcome. Sometimes people use the word partition. This can be used interchangeably with clustering. But clustering is different from cluster. So please be careful with the use of these terms. Then let's move back a little bit and take a look at this unsupervised learning as a whole. We have many different unsupervised learning topics, such as clustering. That's what we are doing now. Next week, we will do dimension reduction. And another very useful unsupervised learning topic is anomaly detection. And we also have some other topics such as association rule learning. There are actually more of them. And in the old days, unsupervised learning was kind of predominant. When you talk about machine learning, many people assume that you're doing supervised learning. But these days, unsupervised learning have been getting more and more popular. So we need to know something about it. And next, to get a better understanding, let's take a look at the mathematical frameworks for both supervised learning and unsupervised learning. For supervised learning, as a game, we're trying to find a mapping, go from the input x to the output y. So you can see y equals f, that's the function or the mapping. Then x input, that's the input of that mapping. And there's another theta. Theta is the parameter or parameters that we use to parameterize that mapping. So for the functions that are defined by different parameters. And the theta, we use it to represent those parameters. For unsupervised learning, now it's different. Here I wrote it as x equals something. Actually, it's not accurate. It should be x approximately equal to something. Here, h is another mapping that we are trying to create. But since now we have no y, so what we are trying to do is just trying to find a new way to structure the unlabeled samples, the unlabeled input data. So we go to a mapping from x to another x. But you may ask, oh no, can we just use it directly? Can we just say, hey, the mapping just x equals x, there's no function? That is, we can do it in that way, but it makes no sense, right? It does not help us. The purpose of unsupervised learning or clustering in this case is that we want to find the structures in data. For clustering, we want to see 5 different points they cluster together to form groups. So we want to find that type of structure in the unlabeled data. And to do that, we cannot just say x equals x. Instead, we need to put some constraints in the hypothesis space so that we don't search all the possibilities. Instead, we need to search the areas that is constrained by the additional constraints that we put in there. So that is for unsupervised learning, and you will see that. And another thing we need to do in both supervised learning and unsupervised learning is that we need to come up with an objective or loss function, because we will also involve in the optimization process to find the best model or the model that can best fit our purpose. Here, how to define which one is better or which one is the best, we need to resort to the objective or loss function. Here, the loss function, we do it in this way, a very typical way. For unsupervised learning here is that we have a new mapping h parameterized by theta as a function of x minus x, and see the difference between them because they're not the same thing. And we want to make sure to minimize this difference. Regarding how many types of clustering algorithms that we have, usually we can categorize the clustering algorithms into several major categories. If you look around, you will find that sometimes people say that there are 4 major categories, sometimes there are 5 of them. And depending on how you do the classification, you may get slightly different classification systems. And here, this is the system that we use in our lecture. We have 4 of them. The first one is centroid based. That means for each cluster, they have their own center. Then we define which cluster a point belongs to based on the relationship between the point and the center. Actually, usually we need to compare the distance or the connectivity or the linkage between one point and the centers of all the clusters and see which one is the best. Usually we use the one with the shortest distance. That's the centroid based. The other one is density based. So for this one, what we are trying to do is that if you take a look at the typical clustering problems, you will find that we have points with different groups. But a common characteristic that we can observe is that for a typical cluster, usually if you go towards the center of that cluster, we will have more denser and denser points, right? Higher concentration or density of points at the center. But as you move away from it, the density will become smaller and smaller, right? That's kind of a common observation. And then density-based clustering algorithms are proposed based on that algorithm. So usually what we typically do is that we try to search for the regions with the higher or highest densities. And for that purpose, we may involve something like a sliding window or something, let them move, or we do it in different ways. Or another way to do it is that we define a few terms to see that how small region, how many points in it. Then depending on how if it has enough number of points in that small region, we may say that a point is like a core point or is something a border point or something is just like an outlier. It's a noise point. So these are just different ways of doing the density-based clustering. And the third type is distribution-based. For this one, it can be similar to the first one, to the centroid one, because it may also have a center. But now the way of doing it is kind of more complicated. Now we do it is that instead of say do it purely based on distances, now we assume that every cluster has its own possibility distributions. So when you get to the center of the cluster, it's more likely that a point will appear there. So that's why we have more points in close to the center. When we get away from it, we have less and less points. That means a possibility that a point will show up, data point will show up there, become smaller and smaller, right? So that forms a distribution. We use a Gaussian distribution or normal distribution for that. We can also use some other distributions. So if we use a Gaussian distribution for each cluster, actually for each attribute of each cluster, then we will have the Gaussian mixture model for Gaussian mixture theory. So here should be model GMM. The last one is hierarchical based clustering. For this one, we can do it in two different ways. We can go bottom up. We call it agglomerative. That is, you take a look at all the points. Then you see how to do it. Try to combine 2 points first, and then combine another 2 points based on distances. A straightforward way of doing it that you combine the points with the shortest distance between them. And then you combine the one so they form a new point, and the center is now the new combined point. Then you keep doing that. Eventually you will combine everything into 1 point, right? But we will not do it in that way. We will set up a threshold. Say that when you get to 5 points, then it's done. And then you take a look at 5 points that you get, and each point is combined by many other original points, right? That's kind of the cluster. So that's how we do it. And the divisive one, top-down one, is done in the opposite way. In that one, we assume all the points that form one cluster. Then we find a ways to first we chop it into 2 pieces. Then keep doing that until you reach the number that you want, how many clusters that you want. So that is the hierarchical based force clustering. Some people also call it connectivity based clustering. And for each of them, you can see that at least a few common algorithms. For centroid based, we have k-means. That's the most popular one. And we also have another popular one called a mean shift. For density based one, we have dbScan and optics. And in this lecture, we will talk about dbScan. For distribution based one, we will spend most of the time on GMM. And for hierarchical based one, we'll talk about the agglomerative hierarchical clustering, or it's called AHC. Sometimes it's called hierarchical agglomerative clustering, HAC. It's the same thing. So let's take a look at the first one, k-means, to see how it works. And on the right, actually, I showed a plot. In this plot, it involves only 4 iterations to cluster 3 groups of points. So you can see how it happens. But I want to first take attention to the equations on the left. So what we need to do for k-means is a k here, that's the number of clusters that we want to get. So for k-means, in order to implement it, first thing we need to do is need to determine how many clusters that we need to eventually want to get. Actually, in many other clustering algorithms, some of them that you don't need to specify how many clusters that you want to. But for some of them, like k-means, we need to specify how many clusters that we need to obtain. If you say that I want to get a 3, then you will only get a 3. So for this one, K, capital letter K, that is for, so here, sorry, this should be capital letter K here, from 1 to K to capital letter K here. And mu, you can see I put a vector sign on top of that one. That means it's a vector that we use it to specify the location of the centroid or the center of the cluster. So in this one, we have a capital letter K centers for capital letter K clusters. And each center has a vector to represent its location. Here is the mu1, mu k, mu capital letter K. something we need to specify at the very beginning. And next, let's take a look at that mapping h something. We use h parameterized by theta of the function as a function of x. We did that, right? Now we use the theta here, the parameters that we need to define the algorithm, the mapping here is mu. So h is the mapping that we define by mu from x as input. The output is also x. And so what's the meaning of this mapping here? It's defined actually by the equation. This is the hard part to understand. So here this equation. Can you guys understand the meaning of the equation? What does arc mean? So if there's no arc, that means that we need to minimize something, right? And there's the arc, that means we need to find parameters that can help us minimize something. Here we are trying to try to find what's the parameters that we try to find. That's mu, right? We want to find the parameter mu that will help us to get the minimum value for this distance between mu and x. X is any point. You have a clustering task, you have many data set samples, you have many points, so each of them is represented by vector x, right? And here we want to find a mu that have the shortest distance with x. What does it mean? Mu, that's the location of a center, right? So we want to find a center that is closest to the point of interest, right? That's actually what this mapping does for us. If you see something like this, make sure you understand the meaning of it. This something means that if you're giving any point x as the input, what the mapping will give us is the closest center to this point. So you give one point, you have capital K clusters. Let's say you have 5 clusters, then you're going to have 5 centers, right? You need to calculate the distance between this point and all the 5 centers to see which one gives us the shortest distance. That one is the mu. That's the vector represents the location of that center. And and the h mu will give us that mu. So that's the meaning of it. Next, the loss function for any point. That's not for all the data points, but for one point, vector x, because all the point we use the bar, capital letter X, right? For one point, that's the whole unlabeled data set. But for one point, we use a vector x. So you can see that the loss function for one point is to get the distance from x to the nearest center, right? So that's the loss for any point. And then we write it in another way. Instead of writing this way, another way I'll write it, which is easier to understand, is that loss function for any point is that we calculate the distance between this x with all the values here, and then find the minimum one. That's a different way of writing this. It's the same thing, right? So with this new way of writing the loss function, next the whole clustering problem using k-means can be represented using this equation. So because here this is the equation just for one point x. Now we have capital letter I points. So we need to add them up. So first we calculate the distance between any point I with its nearest center, and then we want to add all of them up and then divide it by the total number, so we get an average. And the whole clustering task, the goal of it is just minimize this average distance. So this is a mathematical description of k-means. But you may say, hey, it's still a little bit hard to understand. Let's explain it using one example. So take a look at this figure on the right. We have 4 iterations. At the very beginning, we got something, actually, at the very beginning everything should be black. There's no labels. We don't know which class or point belong to. So what we do, usually we want to initialize the mu. We want to randomly select the locations of all the centers. Let's say that in this case, obviously, we want to go with the cluster number of 3, right? We want to do 3 clusters. So K, capital letter K equals 3. Then we want to select 3 points as the initial locations of the centers. So we do it in this way, 1, 2, 3. If you do it another way, next, we want to see which cluster each point belongs to, right? Based on the distance. So we calculate the distance for this one. You can see that, what kind of distance? Oh, this one is close to it. So it belongs to this blue cluster, right? This all these points blue, but for the points here, you can see that it's here, and all these points are close to it. So they are belonging to the second one, the orange group. The third one is here, so you can see that these points are close to it, so they belong to the green group. And here, this point is still close to here, so it belongs to the second one. Let's call it cluster 1 blue, cluster 2 orange, cluster 3 green. Does it make sense to you? This is actually the result generated by code, so it's a real thing. So this is the first iteration. And then after we get a new clustering, next step, now you can see that the blue ones, these points belong to it. So next ones, for all the blue points, we can calculate the new center of the cluster. And you will find it will not be here. There may be something here. See that? So for the orange one, we will all do the same thing because you have orange points here and here, and if you do the center, it may be somewhere here. And if you go to the next iteration, yes, it is here. And for the green ones here and here, so if you do the average, then it could be here. And then you come here, it's here. So we get the new locations of the centers. Then you get the new locations of the centers. We can repeat the process. We can see which cluster all the points belong to. And you will find the new clustering results in the second iteration. So you can see that now it's different from the first one. When you get the new clusters, now we want to calculate the centers again. To calculate centers, it will be slightly different from the previous one. Here you can see that it moved a little bit. But gradually we will see that the clustering results getting kind of, because this is a very easy problem, we can see that they're getting better and better. And in a specific iteration, you will see that the results will not change anymore. That means it is done. So we reached the solution. And this is for k-means. So this is the process. Make sure, even you cannot understand the equations on the left, make sure you can describe it using your own words. Just close your eye and imagine how you're going to do it. First, get all the points everywhere. Just select the capital letter K number of points, locations for all the centers. And then classify all the points based on the centers, based on their relationship with the centers. And then after do that, you know what cluster each point belongs to. So you can do the center and then use the center as a new location for the center. And keep doing that. That will help us gradually approach the final solution. So that is k-means. And here shows the pseudocode for doing this. You can see that the input is the data set X. We have capital I samples, so go from 1 to capital letter I. First step of doing this k-means is to specify the locations of the initials for the initial center locations. So this is the initialization. We do it here. We use this random choice. Actually, this is the function we have it in Python and also NumPy. So what we do is that we select a number from here. Is that X go from 1 to capital letter I. So we try to select sample from all samples. And next we repeat until convergence. We assign point cluster. So this one will give us the label, right? It's kind of which cluster a point belongs to. And it's based on the minimum distance. For any point, we calculate the distance between this point and all the clusters and see which one have the smallest, shortest distance. And that one gives us the cluster result. That's yi. Next, we want to compute the new centers after the center location. We can use a mathematical function like this. So mu k is the new location equals. We add actually here I is a very special function. That is when yi equals k, then it will be 1. Y does not equal k, it will be 0. That means we calculate for any point. You take, for example, you want to calculate this which it belongs to category 1, 2, 3. If it belongs to category, then we calculate for all the points belonging to cluster 1. What we want to do is that we add their coordinates up, then do the average, so we kind of give the center. So here, depending on which cluster we're talking about, and for example, we are doing for cluster 1, 1k equals 1, 1. Then yi equals 1, that means we're only considering the points belonging to cluster 1, right? So 1, then for points does not belong to cluster 1, this will be 0. So we add all the coordinates of all the points belonging to cluster 1, and here's the number of such points. We divide this average by the sum by the total number. We will get average. That's how to get the centers. So that's how we do k-means. But for k-means, we need to know that it may have some issues. The first issue that we may have is the initialization process. Sometimes it could be sensitive to the how we do the initialization. Here you can take a look at the plot on the right. Here's actually the same example, the same set of data points. But now the problem is that we do the initialization in a different way. We select different locations for the 3 centers at the very beginning. You can see that if we do it in another way, in this case, the clustering is not done yet. Or sometimes it will never be done. So in this case, it's not done yet. So you can see that when you select different locations compared to these two, the 3 locations, initial locations, they are here and here. But in the past one, they are here. They're different, right? So the k-means implementation and outcomes are sensitive to the initialization conditions. And there are different methods have been proposed to deal with this problem. And one of the most popular ones is something called k-means plus. So this is the pseudocode for doing that. I can go through it very quickly so you can get an idea of it. It involves some more random numbers, some probabilities, so that we can avoid the issues that we may have with the sensitivity to initialization. So you can see that what this algorithm does is this one is not a k-means. We don't use it to replace it. It's just for initialization. So we still have the input, that data set xi goes from 1 to capital letter I, and output here is not a classification. Output is mu k. That's the centers of all the clusters. It's actually how we do the initialization. And for this one, we first also need to initialize 1 point. So we call it mu1. For mu1, random choice. So we select 1 point from all data points. We just select one randomly. Next, we need to find the locations for k centers, right? So starting from the second one to the capital letter K clusters, we're going to use this process. We first compute the probabilities of selecting each point. So, for example, in the second iteration, we want to get a location for the second center. For this one, we also want to select from the existing data points. We already selected one for mu1. For the others, we will calculate the possibility of that every point will be selected as the center, initial center. So we're going to calculate this pk, and we will do it for every point. You can see that here xi and mu k is smaller than k, and this is just one of them, and this is for all the point belonging to all the categories. So we do it in this one. Eventually, we will get a possibility of every point of being selected as a second center, and we keep doing that. Then next step, we select the next center given the probability. So you can see that we want to select mu k, for example, k equals 2, the second center. We also use this random choice, but now the random choice is a little bit different. If you go to NumPy, you will find this function. We want to select 1 point from all the data points, from 1 to capital letter I. But each point have a different possibility that is calculated from the previous step. For example, if you have 10 points, the first point being selected for second center is point of 10%, second one 20%, 30%. So we draw 1 point based on different possibilities. That's how we do it. In this way, we kind of give this initialization process more randomness. That will help us avoid the initialization issue. Another problem that we have is the selection of cluster numbers. As I said, for the implementation of k-means, we need to specify what's the number of k, how many clusters that we want, right? And sometimes that may not be easy, because if you have a 2D problem, you can plot everything out, you can see, oh, they roughly form like 3 clusters. let's say that you have a 10-dimensional problem. How are you going to do it? There's no way to visualize it. You don't know how the points distributed, right? In that case, how to tell how many clusters that we want? It's hard. Actually, one purpose of using clustering is help us to better understand the structures within the samples. So we try to do that to understand the structure of the sample. But to get a better K number, we need to understand the structure of it. So there's a paradox. It's like chicken and egg thing. You want to do the clustering to understand data, but you also need to get a good understanding of the data so that you can find the good K numbers for performing the clustering. And in this case, there are no perfect solution to this issue, but one way that we can consider is something like this. For example, for very simple problems, this is what we can consider. We can try different cluster numbers and then plot the variation of the loss with respect to the number of clusters. In this case, you can see that we have 1 cluster, 2 clusters, 3 clusters. And if you can easily find a point which corresponds to a certain cluster number, at that point, if you keep increasing the number of clusters, then the loss will not change too much. That cluster is likely, what you're looking for. In this case, that's actually for the example that I just showed. We do it in that way. We'll find out, when we get to constant number of 3, it seems that the loss function is will not change too much. You keep increasing the constant number. So 3, that may be what we're looking for. And if you take a look at that example, obviously, it forms like 3 major clusters, right? So this method works for this simple case. And for the advantages of disadvantage, K-means overall is a fast method. It's very simple to implement, and it does not involve very demanding computations. But the disadvantage, first, is sensitive to the initialization. Second, the selection of K can be tricky. But we have method K-means plus. We have that new method for determining K. They work okay for simple cases, but for complicated cases, the determination of K can still be tricky. This is the first centroid-based clustering algorithm. The second one, also in the centroid-based clustering category, is called a mean shift. So for this one, it also involves a iterative process, and in every iteration, you can see that here we have different grid points. Even different grid point is also a center. Every center is the center of a circular sliding window. And we will take a look at each of those sliding windows. So in every iteration, this sliding window will move, will shift from one point to another point. And the shift of every single circular sliding window will occur towards a denser region with more points or a high concentration of points. And this shift is achieved by replacing the current center with the mean of the points within the window. So it's kind of similar to what we did in K-means. So in K-means, we want to use the new center to represent the current one. Here we do it in the same thing, but we also want to move the window as well. And for any sliding window, it has parameterized by the location of center, and also another thing, that's the radius. That's the size of the window, and the size of the window is a hyperparameter that we need to specify at the very beginning. So this process is continued until every point is passed by at least one window. So we need to make sure that we have enough grid points, enough initial locations for the sliding windows, and to make sure that in every point, every original data point will be passed by one. And when we are moving the sliding windows, we will do one thing. That is in every step, we want to see what point that window covers or passes. So for example, cover that point in one step, we will say that point is visited by that window once. When to move next one, if it's still covered by that window, we say that it's visited by that sliding window twice. So we will calculate the total number of times that a point is visited by a sliding window. Another thing is that you can see that at the very beginning we have a lot of sliding windows, and if we do it, we will find that all the sliding windows, you see that at the very beginning points are here, but all of them move together towards some denser regions that correspond to different clusters of points. And when they get closer and closer, they may merge into some of the points. They may merge into one point or one sliding window. So then we also need to update the visit statistics in that way. For example, this point is visited by all of these points once. When they combine into one, we say that is visited by, for example, if there are like 1, 2, 3 points, and if one point is visited by one window once, the other two twice for each of them, then we say that it was visited by this combined window 5 times. So that's how we calculate the visit statistics. At the end, how we determine the cluster is based on this visit statistics. We can, for any point, we see how many sliding windows we have at the end. Let's say that we have 1, 2, 3, 4 sliding windows. Then we want to see for this point how many times it has been visited by any of them. For example, this is 20, 15, 10, 3. Then we said this one 20 has the highest number of visits, so it belongs to this one. So that's the idea of mean shift. I can show you the process. This is you can see that the centers, sliding windows, they're shifting towards the denser regions, and different sliding windows they combine into one. At the end of the process, we will record the number of visits that each point will get from different sliding windows or combined windows at very beginning, at the end. We want to count how many times that one point is visited by each of the 4, in this case 4 combined windows, and select the sliding window that have the highest number of visits as the final cluster. Did you guys understand this? So for clustering, it's very interesting because you can propose your own algorithms as well. Usually it's based on a very simple philosophy and it involves an optimization problem. Here it shows the movement of a window. This is for one window, and this is the original red point. That's original location, and it's moved towards a location with higher density. The way of doing it again, as I said, we know the initial location, we know the window, we calculate how many points in it, then we do the average of the locations of all the points inside that window, use that average as a new center. So new center will be different from the original one. So you will see a movement from here to here. They keep doing that. That is the mean shift. And in more advanced implementation of mean shift, people add kernel functions that we learned about before. So kernel functions, instead of to get the center of data point, one way is just do the average. That's a very simple one. Another way of doing it is doing it based on the total density. So believe that for every point, it has its own density distribution. So right at this point, high density, when you move away from it, the density gets lower. So in this case, it's not like say that if we don't use the kernel function, we only have density at one point, nothing between them. But if we use density distribution, now everything becomes continuous. The good thing is that if you use density distribution, we can add them up, get a total distribution. So now in order to determine which direction that we want to go next, we calculate the gradient in the density distribution. We wanted to move it from higher density, right? We want to move to a denser area. So we use that to determine which direction that we should move. So that will give us a smoother implementation of this. And the advantages and the disadvantages. So for advantages, mean shift does not require us to specify the number of clusters as what we need in k-means. You can see that we just need to specify the initial centers of all the windows and let it move and eventually be combined into several combined windows. And if we find that some points are not visited in that process, we need to add more seed points and create more sliding windows and repeat the process until all the points are visited. So we do it in that way. So we don't need to specify the number k. A disadvantage, the selection of the window size may pose some challenges and it can be trivial in some processes. That's a hyperparameter. So use different radius for the windows. Obviously, you may get different results. And we just finished the first category. The second category is called density-based, and one of the most famous one in this clustering algorithm in this category is called a db-scan. db-scan is a little bit hard to understand because this one introduces a few more concepts. Here, I just want to give you guys quickly go through this and leave you guys an impression what they are. So first thing is called epsilon. Epsilon defines the neighborhood around a data point. So 2 points are considered to be neighbors if their distance is smaller or equal to the epsilon. So you say that point 3, calculate distance. If their distance is smaller than that, they're neighbors. If their higher distance is greater than that, they're not neighbors anymore. The second thing is called P, is a new parameter. This is the minimum number of neighboring points within a radius of epsilon. So for example, if the distance is here, for example, 3 points, you draw a circle. If you have 3 inside it, what define a minimum number? If 3 is a minimum number, that means these 3 points satisfy the criterion. So NP is another thing that I want to define. We use NP because we want to define a few more things. Data point. First, it's called a core point. Here we use the green, red color represented. If a core point has more than NP points within distance epsilon. So for this point, we'll take a look how many points within the distance of epsilon and in the vicinity of this point. If, for example, if NP is 3, if there's 3 or 3 more points, then we say that, oh, this one satisfies the criterion of core point, so it is a core point. If it has less than that, it's not. A border point, here we use a yellow color to represent it, has less than NP points within epsilon, but it is still in the neighborhood of a core point. Neighborhood, again, we define it in this way. It is within the distance of epsilon of the core point. A third type of point is called a noisy point or outlier. Is neither a core point or a border point. Here, the plot here shows one example of 3 points. You can see that the red points here that are close to each other. For each of them, there's at least 3 points in the vicinity. And this yellow one does not have 3. They only have 1, for example, but it's still close to the red point. But the blue point, you can see that it does not have any point in the vicinity of it. If you draw a circle, there's no points in it. And it's far from all the core point. So it is a noise point. So in this way, we can define 3 types of points. One more concept that we need to understand is something called density connected. 2 points are density connected if they are within the neighborhood of a core point or the connected neighborhoods. So that means if A and B, they are within the distance of epsilon, then we say they're connected. Or if they're connected and this one connected to the other one and connected to the other one, eventually we can use a chain rule, saying that this one is connected to this one as well. The 2 yellow ones, because they are connected to different core points, and these core points, they are densely connected as well. So we can apply the chain rule. Then, based on the introduction of all these new concepts, they may be a little bit hard to understand, but they are the way that help us to implement the DB scan framework. So based on this, we use the steps to do the DB scan. First, we identify all the neighbor points within epsilon and mark the core points. Next, we create a cluster for every core point that has been assigned to a cluster. So if you do this thing, you will find that some points, they are clustered together. You have core points, you have border points on the side. You have some others, you have core points, you have border points on the side. But these 2 new clusters, they are not connected. And so a majority of the points, they may be distributed in one of the cluster of 4 points and core points and border points. But there are a few points, they're noise. They're not connected to any one of them. So that's eventually what we will get. And the way to tell which cluster it belongs to, you just need to take a look, see whether this point, which cluster this one is densely connected to, right? Yes.
And here, do we define number of clusters that we want or not?
We don't. We just need to find out which point is the core point, which is the border point. And eventually you can see that here in this example, you can see all of these things, they're connected, right? And there's one thing that is separate from all the other things. So they form one cluster. You can imagine that you have another set of points here. Far from it, they may also be connected to each other, but they are not connected to this noise or the first cluster. So that form a second cluster.
Like this graph, the point that is between A and C, that one, cannot be that one, and the one that is between A and those can be like core points by their own.
So A is the core point, C is not.
Okay.
This one?
Yeah.
This one is a core point. And the red points are core points.
All reds are core points.
Yeah.
Okay.
The yellow ones, they're border points. You draw a circle surrounding the yellow point, there's only one here. So
So it depends on what you're looking for, how many clusters that we want, choose between the core points.
no, the core points is different. For example, for this C, in order to determine whether it's the core point or not, we know the radius, right? We know the epsilon, right? We define it. We draw this one, the radius epsilon. We draw it. And we also define NP. Let's say NP also is a hyperparameter. Usually need to be 3 or greater than 3. So let's say it's 3 here. So you take a look at how many points here. There's only 1, 2. So that means it's not a core point. Then we take a look at C. This point between A and C, the red point, you can see that we draw a circle. You'll find that there are 2 other points within that distance, epsilon. So there are a total of 3 points. So that means the core point. So we mark it in red. We do all the points in the same way. You will see that we have 6 red core points, right? 6 core points. C is not a core point. However, it is within the distance of epsilon of this one of the core points here. So it is the border points. So eventually you can mark everything in different colors. And if you got this blue one, noise point, and all these points, they're either red or yellow. And we find that they are densely connected to each other, right? So they form one cluster. If it's possible that when we have more points, we may have a different cluster here, and all the points are densely connected to each other, but they are not connected to the noise or the points in the first cluster. So in that case, we identify a different cluster. So the determination of NP and epsilon matters. If you can imagine that if you use very small epsilon, what's going to happen?
Noise.
Yeah, every point is a noise, right? If you use very big ones, everyone will be connected. So that will determine how many clusters that we will get. Also, the selection of this NP will also matters. Will all determine which point is the core point and which one is border point. Any other question? So it's a little bit hard to understand due to the introduction of the new concepts, but once you understand it, it's not that difficult. It's just new. So the process is just like what I said. So I think I explained the process, so we don't need to go through this again. So you can see that that's how it works. So you can see, oh, this point is connected to that one, and keep going, and eventually they can be connected. And then this is the second cluster. You can see that, oh, they connected most of the points here, right? But you can see that this cluster here, it will not be able to be connected to the points here. So they form 1, 2, 3, 4 clusters, and there are many data points that will not be densely connected to any of the clusters. So second is the second cluster, third, fourth. Oh, they got a lot of noise. All right, that's it. And for advantage and disadvantage, the DB scan is good because it can handle arbitrarily shaped and size the clusters. So if you go back to the previous one, you can see that it form a very strange cluster shape. It can handle that because it's not based on previously k-means. Everything need to be compared against the distance, be evaluated for its distance to the centers. So that in that case, you may only deal with clusters with a circular shape. But this one is not necessarily the case, and does not require a preset number of clusters. As I mentioned, it depends on selection of the numbers NP and epsilon. DB scan can be used to identify outliers as noise. This one could not be done in the algorithms that we introduced before. But also there's some cons that we need to pay attention to. It may not be very effective in the case of clusters with varying densities, and the setting of epsilon and NP can be tricky, especially when there's a change in the density levels. And the determination of epsilon in high dimensional data can be challenging. So these are the disadvantages. The other one is Gaussian mixture model. This one is also a little bit hard to understand, but you can understand it in comparison with the k-means. For k-means, we only need to consider the distance, and then see which one has shorter distance. But now we need to consider the possibility of belonging to the one category. Use a process called expectation maximization, EM. And for one, the typical procedures like this. And now different from k-means. In k-means, for any point, we say that it belongs to either cluster 1, cluster 2, or cluster 3. But now the situation is a little bit different. Now we are talking about probabilities. So for any data point, it may have a certain probability of belonging to cluster 1, and it also have another probability belonging to cluster 2, depending on the distance of this point to the 3 clusters or the center of the clusters. And we use different distribution functions for doing this, but in GMM we are using the normal distribution or the Gaussian distribution. For Gaussian distribution in a one variable case, that means all the data points only have one attribute. In that case, we're gonna need to use only mu, the mean, and the standard deviation, that is sigma, to represent one normal distribution for the distribution of point within one cluster. If we have 3 clusters, then we need to have 3 sets of mu and sigma values. However, in most cases, we not only have one variable, so we have multiple variables here. That means we have multiple attributes. And for multiple attributes, then we need to have multivariates, normal distribution or Gaussian distribution. In that case, we still need to have mu, but mu depending on how many variables you have. If you have 2 variables, you can plot every data point in a 2D space, right? Then the mu, the location for the center of that cluster, also have 2 coordinates, right? So you should have 2 for every mu, for every cluster, you should have 2 values instead of 1. And now this sigma thing is not the standard deviation, it's not a one number anymore. It is going to be the covariance matrix. So depending on how many variables or attributes that you have, if you have 2, then it's going to be 2 by 2. And there's an equation for calculating this sigma. Mu is just the mean, and sigma, we can use that equation for calculating the covariance matrix. So you can see that the first step in this EM process is to assume the distributions depending on how many clusters you have. You have 3 clusters, you need to assume 3 different normal distributions for the 3 clusters. And for each of them, we just need to figure out the mu as a vector and sigma as a 2D array for each of them. That's the first step. The second step is to calculate the probability of each sample or each data point belonging to different groups. For any point, you need to calculate the possibility of this point belonging to cluster 1, cluster 2, and cluster 3, because there are going to be 3 probability distributions for the 3 clusters. To do that, we just use the 3 Gaussian distributions that we assumed in step 1. In each of them, for any point, we can get a probability. Here we use n to represent the probability. Here xi, that means that's for data point I. We can get the probability of it. Step 3, we need to calculate the contribution of each distribution to the generation of the data point. Because we know that now for any data point, it does not belong to any cluster. For sure, there's possibilities. So it may have 40% of probability belonging to cluster 1. So to do that, we need to calculate the contribution of different distributions to one point. To do that, we need to calculate this gamma k. That means this gamma ik is the contribution of the distribution or cluster k to the data point I. With this gamma ik, next what we need to do, we need to update the Gaussian distributions with this gamma ik. That's like what we did in k-means. When we know what data points belong to this cluster, we need to calculate the new mean and use the new mean to replace the previous center. Here we do it in a similar way, but the difference is that now everything is not deterministic. We don't say that it belongs to 1 or 2. We update the possibilities of data point belonging to different ones. And we use the new contributions of this gamma ik. We can calculate the new mean and the new covariance matrix standard deviation. That's step 4. Last step, because in the previous step we have one thing that is pi k. So at the very beginning, we need to assume this number. But here, we need to update this number based on what we got. Pi k is the weight of the Gaussian distributions. For each Gaussian distribution, they may have an overall weight for how significant that one is. So here we also need to do that. And the way of doing it is very simple. We just add them up. For example, for gamma ik, I can go from 1 to capital letter I. We just add them up, then we get a pi k. And step 6 is just repeat the steps 2 to 5, so that the Gaussian distributions that we assumed at the very beginning can better and better describe the data. And if we come here, you can see that at the very beginning we assume a Gaussian distribution, then it will become more and more accurate as we perform this EM process for the solution to GMM problems. And you can see that there's no clear boundaries. Here we just use the contours to show that there are no clear boundaries. Actually, they're everywhere. But as you get away from the center of the Gaussian distributions, then the probability will become smaller and smaller, right? And the center is determined by mu. And this is a 2D case, so mu should have 2 numbers for every mu. There are 2 mu vectors with 2 vectors, and for each mu vector, there are going to be 2 numbers for the x coordinate and the y coordinate. And how narrow it was, the shape of it, that will be determined by that covariance matrix. You will determine it's going to be like circular or elliptical, or how wide it is. That's determined by this sigma. Next, you can see this one. Actually, this is the real results that was obtained using the code shared in your book chapter. You can see that on the left, we have the data point, the data samples, measure the samples. They have their own labels. You can have different colors that belong to. This is actually a multi-class classification problem with labeled data. So you can see that it belongs to different classes. In this case, different clusters. But then we use GMM to do the clustering. We can see that the results will be slightly different because GMM is based on the GMM algorithm based on distribution, how far the points are from the center. But this is from the measurements. Later on in your lab, you need to do this yourself to get the results. For GMM, it has multiple advantages. For example, it maintains a higher level of flexibility in cluster variance. That means you can deal with the shape of that leaves. You can see that. And it does not need to assume a spherical clusters. For example, for many clustering methods, if you use the Euclidean methods, just like the mean shift one, we use a circular window, right? The shape is determined. We can only specify the radius of it. And we let that circular sliding window to move through the data. So in that case, because we use a process like that, then we assume like spherical clusters in some way. In mean shift, it's not very obvious, but if you go to like k-means, that's very obvious. And we obtain probabilistic estimates instead of a deterministic cluster label. We don't say that it belongs to label cluster 1 or 2 or 3 for sure, but instead we have probabilities. And disadvantages, first we need to assume a distribution. In GMM, we assume normal distribution for the distribution for every cluster. And we need to have efficient data for each cluster because now we need to figure out what the distribution we have. In order to get a distribution, we need to have enough data points. If you have 1 or 2, that's really hard, right? And we also need to specify the number of clusters. This is a disadvantage that is similar to the k-means. And it could be sensitive to outliers and the initialization conditions. You can see that for GMM, we also need to assume the original distributions. That's similar to the assumption of the original center locations in k-means. But now we have to deal with 2 parameters, mu and sigma, or mu and mu is the smaller letter sigma, or mu the capital letter sigma. And another disadvantage is that it could be relatively slow. You can see that now the process is slightly more complicated. And the last category of clustering method. That's the hierarchical clustering method. But in this one, we'll introduce one of them. It's called a hierarchical agglomerative clustering, or HAC. And for HAC, here the procedure actually is pretty straightforward. That is, we start by making each data point a separate cluster. So let's say that if you have 100 points, we assume that we have 100 clusters at the very beginning. Then we measure the distance between any two groups or clusters. In this case, we have 100 clusters to measure the distance between those 100 clusters, those 100 points at the very beginning. Next, we merge two clusters or 2 points with the smallest distance. We have 100 points at the very beginning, right? You know the distances between any of them. Then you select the pair with the shortest distance, and you merge them into a new cluster. So at the end of that merging process, you're going to have 99 clusters, right? And there are 98 individual points, and there's one pair of 2 points because we just merged 2 points. And we can repeat this process so that we can go from 99 to 98, 98 to 97, 97 to 96. And you can take a look at the figure on the right to see how that could happen. In this case, I give out one example. You have with A, B, C, D, F, we have 6 points. So to do that, at the very beginning, we assume that there will be 6 clusters. Each cluster has 1 point. Then we measure the distance between any pair of clusters or points in this case. And we will find that with all of them, A and B, they have the shortest distance between them, right? So we merge these two first. We mark 1. That's what we did in the first iteration. Then second round, we do everything again. So for the new cluster consisting of A and B, we use the center. The easiest way, use the center as the new center of the whole cluster. So we calculate the distances between the new clusters. We repeat that merging process. So then eventually we will have something like this. You can see that A merged the first, then CD second, then the second merging process will occur between the cluster consisting of CD and E. So keep doing that step by step. Eventually all the points clusters can be merged into one super cluster, right? But we don't want to do that. The purpose is to divide it into several clusters. We don't say, hey, now 100 points, we only have one cluster. That does not make any sense. So we will set up something called a threshold to determine where we should stop in this continuous merging process. In this case, if we set the threshold here, then we know that we can have 1 and 2 clusters, right? So E belongs to one cluster, and all the points belong to the other cluster. And if we move it downward, the threshold downward a little bit, let's say that if we put it between 3 and 4, eventually we're going to get 3 clusters, right? One cluster, A and B, the other one C, D, E, and the other one F. So that's how we do it. And this is the agglomerative way. This is the HAC. And we can do it in the opposite way as well. That's divisive. So for that way, we assume that we do it in completely opposite way. We assume that at the very beginning we only have one cluster. Then we want to divide it into 2 and keep doing that. So that is HAC. And here's one GIF showing how everything is done in a dynamic way. You can see that on the left, you can see how different data points are merged. And on the right, you can see how that clustering process occurs. You can see that it shows the thresholds. We put it here. We have 3 clusters, 5 clusters. You can see that. If we put the threshold here, we're going to have 3 clusters. If we move the bar higher, we're going to have 2 clusters. So this is just a different example, very similar. For HAC, advantages are that first, there's no need to specify the number of clusters. But we need to keep in mind that instead we need to specify the threshold, right? But we have different options. If we finish the whole merging or division process, partition process, we can set the threshold at different locations depending on how many clusters that we want. And it's easy to incorporate categorical features. So when we talk about data, some of them, they have categorical features. one belongs to other, something like that. And HAC is good for data like that. And it's not sensitive to the selection of distance metric. In the previous, in the introduction to the previous clustering methods, we mentioned that sometimes we need to specify the distance metric. And the most common one, of course, is the Euclidean distance, but we have some other options. Here, if you try HAC, you will find that it has the advantage of its low sensitivity to the selection of distance metric. For these advantages, first, the number of clusters may be difficult to determine, so this is also somewhat subjective. Second is may not be that computational efficient as k-means. If you do the coding yourself, you find that it may not be that easy to do because every time you need to calculate the distances between any pair of clusters. So that will take a lot of time to loop through all the data points. And every time you may also want to record a lot of things such as distances, such as the number of the points or the clusters. And that's the end of the lecture for clustering.
I think I'm falling for you.